Yeah, welcome back. Let's continue this session. If you see the static resistance versus dynamic resistance, right? I think as I told you, the dynamic resistance is the one which is what is describing about the change in quantity with respect to the change in independent parameters. Okay. Now write down observations exactly similar to your ideal voltage source. First observation, similar to ideal voltage source, is this linear? Is current changing linearly with respect to voltage across the current source? No, current is constant, which we need. Therefore, it is not linear and it is not changing linearly with respect to the voltage. Therefore, this is also not linear element. Write down first observation. Ideal current source is a non-linear element. Ideal current source is a non-linear element. Ideal current source is a non-linear element. Number 2, dynamic resistance is not equal to static resistance. Okay, write down dynamic resistance is not equal to, write in symbolic format because sentence format is difficult, it is easy to understand. As I told you, dynamic resistance or internal resistance, incremental resistance, AC resistance, equivalent resistance, everything is same. We need not write here because which we already represented in the case of ideal voltage source. Okay, dynamic resistance is not equal to static resistance or DC resistance. When you say dynamic resistance, then complementary static resistance. When you say AC resistance, this is what is DC resistance. Okay, is this over? Yeah, these two are our observations. Okay, now write down the third one with which I'll stop and then we can extrapolate. Okay, and then we can have conclusion also. Third one, ideal resistor. Let me erase all these things. I need this. Okay, it's fine. I'll write once again. Third one, therefore let me take, now what is our characterization element? Our characterization element is, let us say this is what is 1 ohm resistor. This is what is my characterization element. Okay, I want to characterize the black box or the element which is what is present inside with respect to what? With respect to voltage and current only. Okay, always we try to characterize with respect to voltage and current only, and we try to take the ratio of voltage to current either static way or dynamic way, either V by I or delta V by delta I. That is nothing but static resistance or dynamic resistance. Don't write, just listen. I'll give you time to write down. Therefore, as I told, resistance means static resistance or dynamic resistance. Therefore, R static is equal to R static. This is what is static. Capital R itself is static resistance is equal to V by I, and this is what is your small r dynamic is equal delta V by delta I. Okay. That's fine. Now I want to characterize with respect to voltage and current. Do you have voltage? No. And do you have current? No. And let me tell you why it is different. Means I can say simply resistor, but I am saying ideal resistor. What is the meaning of ideal resistor? What do you mean by ideal resistor? Or what do you mean by practical resistor? Right? Okay. If I don't add the term called ideal, then remember whatever 1 ohm I told, that 1 ohm will change with respect to temperature. That 1 ohm will change with respect to what? The tolerance. Because when you purchase a resistor from the market, then I think no need to purchase from the market. When you do any lab, right, in the lab, if you ask for the resistors from the in charge, he'll give you a resistor, but we have something called color coding, right? That color coding is indicating the value of resistor plus the tolerance. Means when I say 1 kilo ohm resistor, it will have plus or minus 10% tolerance. Means it can be 900 ohm, it can be 1.1 kilo ohm. Means it can be 900 ohm or 1100 ohm, about 1 kilo ohm or about 1000 ohm. That is what is called the tolerance. Means the practical resistor will have tolerance, practical resistor value will change with respect to temperature. Let me ask another question. Is the resistance value depends on frequency? Means let me apply a voltage across this resistor, and the voltage is a sinusoidal waveform. Means it is basically AC signal, right? Therefore, is the frequency of voltage source and the current what you are going to get from the voltage source, which is what is flowing through the resistor, basically the frequency of excitation will change the resistance value? I'm asking you. Is resistance value function of frequency? We know that the resistance is function of, your resistance is function of what? Your resistor. This is what is function of what? Temperature. That is what is function of temperature, right? Therefore, let me say, if you take any resistor, right? The resistor value, let us say this is what your R, 1 ohm. Can I say this is nothing but function of what? Temperature and the variation. That is what people call as process variation, or practically you know this already, tolerance. And is it function of frequency? Strictly speaking, this is also function of frequency, but which we will not consider. Why we will not consider? Let me tell you. I think everybody knows why it is function of temperature, right? And we know that, right? If you take temperature parameter, we know that is nothing but temperature coefficient, right? Which is alpha. That is nothing but R2 minus R1 divided by R1 into T2 minus T1. Means if temperature changes, your resistance changes, that is what is your alpha, right? But when I speak about ideal resistor, alpha is 0. Alpha is 0. What does it mean? Even though there is a change in the temperature, if there is no change in the resistance value, R2 minus R1, if that is what is 0, then your alpha is equal to 0. This is what is ideal case. What I want to say here is, when I characterize, I am characterizing with respect to voltage and current, and independent of temperature, independent of the tolerance, it is only 1 ohm, means 1 ohm only. There is no change in the resistor. And frequency means with respect to frequency, the resistance won't change. But if you take your network analysis, we always take resistor, let us say 1 ohm resistor. We will not think that the resistor will change with respect to frequency. We will take it as it is. But if you take your capacitor and inductor, they are frequency dependent parameters. The reactance of your inductor and capacitor changes with respect to frequency, right? But in the case of resistor, we will not take that resistor is function of frequency. But strictly speaking, but not at low frequencies, and at very high frequencies, your resistance, right, is function of frequency. I think you already studied this point from electromagnetics, right? EM theory. What is that? If you take any transmission line, basically your transmission line is also nothing but what? It's a wire having some length, having some area of cross section, and it is a material. It can be iron, it can be copper, it can be anything, right? Therefore, it is a material, then it is a wire, let us say, then it will have resistance, right? R is equal to rho L by A. It will have some resistance. Therefore, you can treat the transmission line as a resistor, right? That resistance is nothing but low frequency resistance. But strictly speaking, as the frequency is increasing, as the frequency of excitation is increasing, right, the resistance whatever you offered, which is low frequency resistance, which is R is equal to rho L by A, that is no more valid, because there is something called skin effect. What is skin effect? Whatever wire you have, which you are representing with a resistor, because it is associated with what? It is associated with area of cross section and length of the wire L. Then you are saying that this R is equal to rho into L by A, where L is nothing but length of the wire, A is nothing but area of cross section, rho is nothing but resistivity, which is 1 by conductivity. Therefore, that depends on the type of material, okay, which is fixed. If type of material is fixed, conductivity is fixed, therefore resistance is fixed. But remember, as the frequency, let us say this is what your transmission line, one more line is there, we are exciting at the source, right? Then that is what you are trying to transmit the signal, and there is a receiver and we are receiving the signal. Remember, if the excitation frequency is very high frequency, then whatever resistance you told, that is not valid, because your resistance, there is something called skin effect. What is skin effect? At very high frequency, I am not going into too many details about skin effect, but let me explain what is skin effect. Therefore, at low frequency, let us say your frequency is equal to 0, means, what does it mean? DC signals. Therefore, for DC signal passes, therefore when you apply DC voltage here or DC current when you are trying to pump water, whether it is voltage or current, DC signal means are low frequency signal. Your network analysis, whatever you are doing, assuming that the resistance is not function of frequency, means even though you are doing AC steady state analysis or AC analysis and all, or AC frequency response analysis, excuse me, and there we are assuming that the resistance is not function of frequency, therefore it is considered as low frequency analysis. That is what your network analysis, okay, not in the order of hundreds of megahertz or gigahertz and all, okay. But if you consider hundreds of megahertz and in the order of gigahertz and all, then this matters, means the resistance is function of frequency. Then if you take it, right, then whatever cross-sectional area, I am just taking the cross-sectional area, therefore all your electrons, the free electrons which are there in the conductor, right, or a wire or any material, they will be spread across the cross-sectional view of your conductor. Then all your carriers or electrons are moving from one point to another point. That is what is through drift component, drift velocity component, because of the voltage or because of the electric field what you have inside the wire. Now, when the electrons or free carriers, whatever you have, when they are moving, right, with area of cross section of A, and this is what is the resistance. But remember, when you take the frequency very high, right, then it is not DC signal, it is AC signal. Therefore, this is nothing but AC signal. If you take AC signal, right, then if you ask me, the electrons which are trying to flow throughout the cross-sectional view of the conductor, that very high frequency, maybe in the order of, let us say, hundreds of megahertz, or gigahertz, okay, then all your conductor, or I can say your electrons will be concentrated to the skin of your conductor. The electrons are concentrated to the skin of your conductor, and this is what is your depth, skin depth, which is inversely proportional to, let us say this is what is your delta, therefore delta is inversely proportional to the frequency of the signal with which is what you are trying to transfer through the wire or transmission line, right. Therefore, if frequency is very high, then the skin depth, therefore the skin depth will decrease. All carriers are trying to move towards the surface and they try to travel only on the skin, and they try to travel from one point to another point. What is the disadvantage, or what is it doing, or what is it saying? If the carriers are concentrated to skin of your conductor, then all those carriers are coming towards the surface, then the collision between one electron to another electron will increase. If the collision is increasing, then the mobility of the carrier, which is what is trying to move from one point to another point, decreases, means your current is decreasing, because rate of flow of charge is nothing but your current. In a given time, the charge movement due to mobility decrement or due to collision increment, if that is what is decreasing, current decreases for the same voltage. Therefore, what happened indirectly? For the same AC voltage, then the amount of AC current is decreasing. Therefore, your impedance is what? Your impedance, or you can say resistance at very high frequency is increasing. Therefore, because of skin effect, your resistance is not constant. At low frequencies, right, your resistance is constant, which you can calculate directly from R is equal to rho L by A, but at very high frequencies we cannot take it. That is the reason why, to avoid all those non-linearities or the practical effects like temperature, tolerance and very high frequency components, I am just making the word or adding the word called ideal, right? Therefore, what is ideal resistor? Irrespective of temperature, irrespective of process variation or fabrication variation, or which is nothing but tolerance, and irrespective of the frequency of the signal with which you are trying to excite and characterize voltage to current. But currently in the experiment, I am just taking DC voltage versus DC current, but even though it is having some AC frequency also, it is independent of the frequency of the signal with which you are trying to excite the resistor, or DUT, device under test. That is what we are trying to characterize. I hope everyone understood, right? Now I can continue. Therefore, when I say ideal resistor is nothing but irrespective of temperature, irrespective of tolerance, irrespective of frequency, right? I can add few more things. Irrespective of any other condition, the resistance 1 ohm is 1 ohm. Similarly, ideal voltage source, right? 10 volts, irrespective of anything, whether it is temperature effect or some tolerance effect or some discharge effect or due to some whatever may be, or the current what you are trying to draw from the voltage source, it should give constant voltage, then only it is ideal voltage source. Means irrespective of anything, it has to give 10 volts. Similarly, ideal current source, irrespective of anything, it has to give 10 ampere. Ideal resistor, irrespective of anything, it has to have 1 ohm resistor. Everybody understood? Right. Therefore, irrespective of any condition, it has to give 1 ohm resistance. If I say this is what is 1 ohm resistance, now I want to characterize. Let's go to our flow, calculating static resistance and dynamic resistance. Right. Now I just explained the meaning of ideal resistor and ideal voltage source, ideal current source and ideal resistor. Okay. Now coming back to V2I, means V2I response. Now let me excite. Now I want to get V2I. Therefore let me excite with ideal voltage source and vary. Therefore now I want to know the current whatever which is what is flowing through the resistor. But remember here my characterization element is resistor, right? Now remember we can excite with voltage source and observe current, or you can observe with current source and observe voltage. Anything is fine, right? What I am saying is the same element, this is what is your resistor, this is 1 ohm, this is what is my black box, right? I want to characterize. I can characterize like this also, which is nothing but excite with current source and then vary the current, then get the voltage. Therefore, get the voltage. Anything is fine, right? Anything is fine, but ultimately I want to have the characteristics of your resistor with respect to voltage and current. Okay? Okay. If I take this scenario, let us take this, because let us excite with ideal voltage source and vary the voltage. It is like regulator power supply, change the voltage and then put ammeter in series, then you can get the current also. Then we can get the relation between voltage to current. Okay. Now tell me, let me draw. Therefore before that let's take 3 values. Now tell me, if V is equal to 1 volt, then tell me what is the current you get. When V is equal to 1 volt, then 1 volt, then you will get 1 ampere, Ohm's law. When V is equal to 2 volt, 2 volt across 1 ohm, you will get 2 amperes. Then V is equal to 3 volt, 3 volt across 1 ohm, you will get 3 amperes. Right? 3 points are enough to get the curve. Therefore now I want to have voltage VI characteristics. Now tell me what is x-axis, what is y-axis. Here in this scenario, what is independent? In this scenario, what is independent? I am speaking with respect to voltage and current only, because remember ultimately I want voltage and current only. We are trying to characterize with respect to voltage and current. For all like voltage source, current source, resistor, inductor, capacitor, PN junction diode, BJT, JFET, MOSFET, etc. etc. Okay. Now, what is independent? In this scenario, the voltage is independent because that is what I am applying, and it can be anything. And dependent parameter out of voltage and current. Current is dependent parameter. Your current is depending on your voltage. Depending upon the voltage, you are getting the current. Okay. But if you take this scenario, remember, current is independent. Whatever may be the current, but the voltage whatever you are getting across the resistor is depending upon the current. You understand? Therefore, it is nothing but that depends on the excitation, type of excitation. Therefore, here this is what is voltage I am explaining for this portion, and this is what your current. Therefore, now tell me, When V is equal to 1 volt, what is your current? 1 ampere, and V is equal to 2 volt. Therefore, as the voltage is increasing, your current is also increasing proportionally, right? And if you say V is equal to 0, I is also 0. Therefore, if you ask me 1 volt, I am getting 1 ampere. If you ask me 2 volt, I am getting 2 ampere. Remember, this is what I am expecting. Then only I can say this is what is constant. 1 ohm resistor is constant. Okay, and this is what is 3 volt. Then I am expecting 3 ampere. If it is 1 ohm, that 1 ohm is constant throughout the experiment, or throughout any voltages whatever you are trying to excite, then you are trying to respond, or you are trying to see the current which is what is flowing through the resistor. Okay, maybe if you plot for this, x-axis will be current, whatever may be the current, what is the voltage, you will get linear relationship, that is fine. Okay, now this is what is the graph which is what is describing the relation between voltage and current. Therefore, VI characteristics we got similar to ideal voltage source, ideal current source, now ideal resistor. Now let's calculate static resistance and dynamic resistance. Maybe if you want, you can write this part like the practical resistor. This is what your, let us say, practical resistor, your practical resistor, right, is function of all these three. Then maybe you can say this is what your temperature effect, tolerance is because of this thing, and this is what is our second one, our frequency effect, that is what your frequency effect, skin effect. You can take these two. Sorry. Just write this, then after that you can write this, then let's see static resistance versus dynamic resistance. Try to write quickly. Over. Maybe if I add here something, Therefore, if you take practical resistor, if temperature increases, in this scenario, maybe if you take real practical resistor, your resistance value increases. Similarly here, as frequency increases at very high value, the resistance increases. But in the case of ideal resistor, your resistance value is constant. Okay? Okay. Now, let's see the static resistance. Let me erase all these things. Okay? Now, static resistance, let us take case A. Case A, voltage. When voltage is equal to 1 volt, tell me what is R? R is equal to V by I. You can follow me, okay? You can follow me because we did it multiple times for ideal voltage source, ideal current source. You can follow me, okay? Now, R is equal to V by I. What is V? 1 volt. And what is current? When V is 1 volt, current is 1 ampere. Therefore, what is the resistance? 1 ohm. Case B. When V is equal to 2 volts, R is equal to V by I. That is the definition, right? Therefore, V is nothing but 2 volts. And what is the current? When V is 2, current is nothing but 2 amperes. Therefore, this is nothing but 2 by 2, 1 ohm only. Then when V is equal to 3 volt, then what is R? R is equal to V by I. Then what is V? V is equal to 3 volts. And then what is current? Corresponding to that voltage, 3 amperes. Then this is 1 ohm. Therefore, irrespective of voltage, right, we are seeing 1 ohm, and that is what is present inside the black box. Therefore, static definition is describing about the resistance or the resistor, which is what is present inside the block, or the resistance of the black box is nothing but 1 ohm. Now, let's see the dynamic resistance part. I hope this is done. You are following me, right? Until I say that don't write, you don't write. If I don't say that, don't write, you can continue with me, right? Okay, now, from this definition, now, tell me, quantitatively, delta V by delta I, right? But if you see here, we are seeing what is dependent. This is nothing but independent. X-axis is always independent, remember. If x-axis is always independent and this is what is dependent, means I want to know what is change in current because of change in voltage. Okay, therefore maybe I can write it qualitatively, which is nothing but what is change in current because of change in voltage. Basically both are same, but mathematically both are same, or quantitatively both are same, but qualitatively, conceptually both are not same. If you take this definition, what is change in voltage because of change in current? But here, what is change in current because of change in voltage? Voltage is independent, therefore independent, and this is dependent. Therefore tell me tell me if you take a change, let us say the change in the voltage, let us say this is what is delta V. What is delta V? 3 minus 2, 3 volt minus 2 volt. Therefore what is this? 1 volt. Then corresponding change in current. See, when I say change in voltage is this, don't take change in current is this. When I say delta V, corresponding delta I, that is what we need to take. Remember, I can take this also. then corresponding change in current. I can take this also, corresponding change in current, right? Whenever I say delta V, corresponding delta V. I hope it is clear. Okay. Therefore delta V, then corresponding delta I is equal to 3 minus 2, 1 ampere. Right? You can take any delta at any point. Okay. Fine. Therefore, now tell me what is delta I? 1 ampere. And what is delta V? 1 volt. Which is basically 1 volt by 1 ampere. Which is V by I. Right? Which is nothing but what? 1 ohm. Your dynamic resistance is also 1 ohm. And your static resistance is also 1 ohm. Both are saying that it is having the resistance in the black box which we are trying to characterize with respect to voltage and current, saying that 1 ohm only. After this, write down observations. Observations, again similar to voltage source and current source. Again, I am just stressing a point. When I say linearity by default, I am just taking with respect to voltage and current. Okay. There is one of the interview problems from one of the IITs related to resistor. Okay. I'll explain that part later on. Therefore, that is the reason to answer that question. I am just stressing a point saying that I am speaking linearity with respect to voltage and current. Remember, okay? If I don't specify in the case of elements, right, linearity with respect to voltage and current. For all your voltage source, current source, resistor, inductor, capacitor, PN junction diode, BJT, JFET, MOSFET, okay, with respect to voltage and current. But for the systems, it is different. Need not be always voltage and current. If you take control systems, right, it is defined with what? Input and then output, right? Then output by input is nothing but your transfer function H of S, right? Then here people, when I say system is linear, here that is with respect to output signal to input signal. You understand? Therefore, there in the case of system analysis, people speak linearity with respect to output voltage to input voltage. Okay? But here in this case, for voltage source, current source, resistor, inductor, capacitor, all the elements, right, electronic elements or electrical elements, we are trying to characterize with respect to voltage and current, and we are trying to speak linearity. When I say resistor is linear, or when I say inductor is linear, or when I say BJT is linear with respect to voltage and current. Okay. Now, coming back to observations, number 1, tell me, is this linear? Yes, the current is increasing linearly or proportionally with respect to the independent parameter voltage, right? Therefore, write down ideal resistor. Your ideal resistor is linear. Write down ideal resistor is a linear element. You have to write in sentence format, okay? Just I am representing that sentence format into ideal resistor is equal to linear. Okay, write down ideal resistor is a linear element. Number 2, what is second observation? Your dynamic resistance is equal to static resistance, right? Dynamic resistance of your ideal resistor is equal to static resistance. And one more important note or observation, I can say note. See, here I am representing x-axis voltage, y-axis current, right? There is no time information. There is no time information. What does it mean? When I say voltage, 1 volt, changing the voltage to 2 in what time? Therefore, indirectly that is nothing but frequency of the signal, right? Means if you here even I am representing like a battery, right, which is 1 volt, 1 ampere. But ultimately I told that when I vary this voltage, indirectly that is what is becoming AC voltage. Even though we are representing with the battery, right, if I add timing information to the voltage changes, that is nothing but frequency, right? The change of voltage or the change of current with respect to time, that is what is your AC signal. Even I am representing with the battery, right? Therefore, if you see here 0 to 1 in some time, 1 to 2 in some time, 2 to 3 in some time, then what is the change in the current? If you change in the voltage in some time, the change in the current with respect to the same time, right? Therefore, here whatever I am saying, timing information is already there, but let me take in all the cases, voltage source, current source, resistor or inductor or capacitor, it is the voltage change or the current change with given in a given time, let us say fixed frequency. I am not changing the frequency in that case. For a given frequency, if voltage is changing, then how the current is changing. Let us say I am keeping voltage 0, I am getting current 0. After 1 second, I am changing the voltage to 1 volt, then I am seeing current 1 ampere. Again after 1 second, changing to voltage 2, I am seeing the current 2 ampere. Therefore, in these characteristics, remember, not only here, you take any characteristics, timing information is not, it is not there, but it is hidden indirectly, okay? But it can be 1 second, it can be 1 minute, it can be 1 hour. After every 1 hour, you may change the voltage, right? But remember, all the y-axis, which is nothing but your dependent parameter, are under steady state. When you change the voltage under steady state, what is the current? When you change the voltage, what is the steady state current? That is what we represent the characteristics, okay? You take BJT, input characteristics, output characteristics, right? Always, when you give some voltage, whenever you get current, when you change the voltage, what is steady state current? Because you can change the voltage suddenly, then suddenly, if you change the voltage, ultimately what is the change in the current? That is what you need to represent. That is what is very important, okay? Therefore, as if it is like DC voltage which we are changing, that is nothing but long time. Fine. Okay, I think I can say enough. Maybe the same thing if I continue for inductor, 4th one inductor, 5th one capacitor, 6th one PN diode, 7th one BJT, 8th one MOSFET. If I continue, you will get it, right? But I don't want to continue till that point. I want to use first 3, I can say elements, voltage source, current source, resistor, to extrapolate to remaining elements. That is what I want to explain, okay? Okay, now write down overall observations, not specific to voltage source, current source, resistor. Now overall observations, okay? Write down overall observations. Overall observations. Can anyone tell what is your observation? Remember, observation could be many, right? Whatever you observed, that is what is the observation. Therefore, what did you observe till now? In the ideal voltage source and ideal current source, dynamic resistance is not equal to static resistance. But in the case of resistor, both are same, right? The same thing, write down. In the case of resistor, both are same because it is linear, okay? But voltage source, current source, they are not linear, which we want. Both are not linear, but both are not same. Write down. Write down. For all non-linear elements, for all non-linear elements, for all non-linear elements, for all non-linear elements, in bracket, for all non-linear elements, in bracket, ideal voltage source, comma, ideal current source, comma, PN junction diode, Remember, PN junction load is not linear. That is what. After completing this, I'll explain why it is not linear, but it is not linear. Okay, write down. Ideal voltage source, comma, ideal current source, comma, PN junction diode, comma, BJT, comma, MOSFET, and all semiconductor devices with PN junction, I'll explain the meaning of this. Okay, all semiconductor devices with PN junction, close the bracket. These are all non-linear elements. Ideal voltage source, ideal current source, PN junction diode, BJT, JFET, MOSFET are all semiconductor devices with PN junction like UJT, thyristor, SCR, PNPN or NPNP, right? These are all semiconductor devices with PN junction in the path, in the current conducting path, okay, or some path. Therefore, or write down, for all nonlinear elements, dynamic resistance is not equal to static resistance. For all nonlinear elements, in the bracket, close, in the comma, dynamic resistance is not equal to static resistance. That is what we observed from ideal voltage source and then ideal current source. The same thing I am carrying forward to PN junction diode, etc. Dynamic resistance is not equal to static resistance. Dynamic resistance is not equal to static resistance. Write down second observation. For all linear elements, for all linear elements, at a given frequency, write down in bracket ideal resistor, inductor, capacitor, but at a given frequency. Okay, for all linear elements at a given frequency. Why I am specifying the frequency? Frequency is nothing but indirectly the time with which the voltage is changing or the current is changing. Okay, therefore when the voltage is changing from 1 to 2 in a given time, therefore I am saying that the time is fixed, means in a fixed time only I am changing, let us say, then what is the change in the current and the steady state current. Okay, therefore that's what, because L and C are frequency dependent, therefore once the frequency is constant, its reactance is constant, because if you take inductor, what is reactance? Magnitude only. XL is equal to 1 by omega L. Excuse me. Yeah, if frequency is constant, omega is constant, then XL is constant. Similarly, mod XC, sorry, this is omega L. Mod XC is equal to 1 by omega C. If omega is constant and your reactance is also constant. If reactance is constant, done. That's why. But in the case of resistor, at low frequency, your resistance is nothing but resistance only. It is independent of frequency. But if you take very high frequency, that is what? Skin effect and all, your resistance is also a function of frequency. But now I am saying at a given frequency, but low frequency. You can say at a given low frequency. To correct it, at a given low frequency. For all linear elements, okay, at a given low frequency, Write down. Dynamic resistance is equal to dynamic resistance is equal to static resistance. Dynamic resistance is equal to static resistance. Dynamic resistance is equal to static resistance. Means dynamic resistance means I am repeating once again. Normally people represent with small r. It is always speaking with respect to the change in voltage to the change in current. Okay? The change in voltage to the change in current. Here the magnitude change in the voltage at a given frequency. Then what is static resistance? Capital R is equal to V by I. Actually, inductor and capacitor is a special case, right? You may think, you may have a doubt, definitely you will have a doubt, saying that maybe even if I say 1 volt DC and you will get current. That is true for your resistor. But if you take inductor and capacitor, right? When I say 1 volt, that is nothing but DC, which is nothing but zero frequency. For a DC, capacitor acts as a open circuit. For a DC, inductor acts as a short circuit, right? To do not have the special cases, which is nothing but at zero frequency, I specified at a given low frequency, but not zero frequency, at a given low frequency, which is not zero. Maybe if you want, you can say, which is not zero. Given low frequency, but not zero. Okay? Then, that's why, special. Therefore, then in that case, if you take inductor, then what is VI? It is nothing but AC voltage, but its frequency is constant, right? V1. And then I, what is corresponding I? Therefore, this is like phasor representation. V, phasor voltage and then phasor current. Only for inductor and capacitor, this is a special case, okay? Then, this is what is valid. Or if it is confusing you, for the time being, maybe you can ignore the frequency part. You can say a resistor, or you can speak with respect to DC voltage also, which is having zero frequency, right? What I want to say here is overall observations. For all non-linear elements, low frequency, high frequency or DC frequency, whatever it may be, right? For all non-linear elements, dynamic resistance is not equal to static resistance. For all linear elements, right? Your dynamic resistance is equal to static resistance. Okay? Maybe you can compare with respect to this. Example RLC, right? You can say another example. Not only resistor, inductor, capacitor and P-type semiconductor, N-type semiconductor, basically intrinsic semiconductor. SC is nothing but semiconductor, okay? Therefore, resistor, inductor, capacitor and P-type semiconductor, N-type semiconductor and intrinsic semiconductor and, or I can say now, means what I want to say here is, your because in the case of non-linear elements, I told that all semiconductor devices, this is also semiconductor device, but there is no PN junction. If there is no PN junction, stand alone. Let us say this is what is my P-type semiconductor, right? It is linear because it is having some resistance. R is equal to rho L by A. Length, area of cross section, the conductivity of P-type semiconductor 1 by P into Q into mu P. Therefore, its conductivity is constant. If temperature is constant, conductivity is constant, then length is constant, area of cross section. Therefore, it is simply nothing but a linear element like a resistor because it is having some resistance value, right? Similarly, N-type semiconductor is also linear. Intrinsic semiconductor, the semiconductor without doping, let us say silicon material or germanium material without any doping, right? Then it is also linear. But wherever you have PN junction, remember, that will give you non-linearity. Very, very, very simple. Wherever you have PN junction, it is non-linear. That's why I told PN junction, BJT, because BJT is having PN junctions inside. MOSFET, that is also having PN junctions. UJT, it is also having PN junction. Silicon control rectifier or thyristor, which is basically PNPN or NPNP, that is also non-linear. Therefore, all are non-linear if there is a PN junction in the path. Okay? Just to differentiate, I told here all semiconductor devices with p-n junction, all semiconductor devices without p-n junction, they are linear. Okay. Therefore, I want to say, therefore these are all the observations. Now write down conclusion. Conclusion is very important. This is what I am going to carry forward continuation part. In the continuation part, whenever we derive something, default we will take like that. Then you may think that why it is like that. The background for that derivation what we do later is this only. Okay, write down conclusion. Based on these observations, conclusion. Write down conclusion or conclusions. Number 1. For all non-linear elements, now no need to write in the bracket because we already specified in the observations. Okay, write down for all non-linear elements, comma, the internal resistance are just a small correction. For all non-linear elements, comma, their resistance should be defined in a dynamic way. Because if you take your ideal voltage source, the static resistance is giving load value, not its resistance value. Therefore, we should define, when I say resistance of voltage source, default dynamic resistance. Similarly, if you take current source, when I speak about resistance of a current source, default dynamic resistance, because that is non-linear. If you take resistor, when I speak about resistance of a resistor, it could be dynamic resistance or static resistance, because both are same. You understand? Because this is linear element. Okay, that's what I'm saying. Write down for all non-linear elements, comma, their resistance should be defined. In a dynamic way. Their resistance should be defined in a dynamic way. Second conclusion, for all linear elements, comma, their resistance can be defined either dynamic way or static way. Can be defined either dynamic way or static way.